Hey everyone, welcome into lecture number 8. Today we're going to talk about section 2.4 of the text, and this is on the product and quotient rules for derivatives. So in the last lecture, we learned how to take derivatives of a number of different types of functions without having to use the limit definition. But one thing that we don't know how to do, or I guess two things we don't know how to do yet, are take derivatives of products of two functions, or the quotient, which quotient means the fraction of two functions that we know the derivatives of. So the way that this lecture is going to go, I'm going to work out the formulas for the product rule using the limit definition, do a couple examples of that, do the same thing for the quotient rule, do a couple examples of that, and then I'll leave you with a few recommended exercises to finish off the lecture on your own. So let's get into it then. For the product rule, really for both of these rules, we're going to assume we have two functions that are differentiable. So y equals f of x and y equals g of x. We'll say, let these be differentiable functions. Remember, differentiable functions means that the derivative exists, right? And we'll say that they're differentiable functions in general. I won't say what point we're looking at, but in general, these are differentiable at the point that we care about. So they're both differentiable at the same point, for example. So you could say, if you wanted to, that this is true at x equals a for some value of a, but I'm going to do it in general for general x values. So for our product rule, we want to be able to take the derivative of the product of these two, right? So what we want to do is take the derivative with respect to x of the function that's built as f of x times g of x. So that itself is a new function now. And we're going to do this again by plugging into the limit definition. And I'm going to use the h definition once again. So the limit as h approaches 0. Remember that the way this works is we have to plug in x plus h to our function. But our function now has two kind of parts to it, right? It's got f of x, which we're going to plug in f of x plus h, times g of x. But again, we have to plug in x plus h to that one, right? And so then we subtract from this just the function itself, which again is built out of its two parts, f of x times g of x. And this is all over h. Okay? So at this point, as usual, we need to do more work somehow, right? And a lot of times the more work we do is trying to eliminate the h that's on the bottom or make some kind of algebraic simplification that helps us solve the problem. In this case, we're going to try to reduce this, and I say reduce, but we're going to add more terms to this basically to try to pull out some terms that we actually know what they mean, okay? So rather than speak in code here, let me just write it out. We can always add 0 to something without changing it, right? So what we're going to do is add something and subtract itself, and then kind of group and do some factoring here. So I'm going to rewrite the first term here, f of x plus h times g of x plus h. And I'm actually I said add and subtract. I'm going to start by subtracting, and then I'm going to add it back on. So what I'm going to subtract from here is f of x times g of x plus h. So kind of a combo of the two things that we have up here, right? But if I subtract that, then I do have to add it back on. So I'm going to add back on f of x times g of x plus h. So everything that I wrote in red there cancels out, and it really doesn't change what we have here at all, right? Then I have I'm going to finish writing this out. So I have to write the minus f of x times g of x, and then put this whole thing now over h. All right? So how's this going to help us? Well, it turns out that we can group the first couple terms and the second couple terms, and we can distribute the limit here and treat this like two different limits and see what happens, all right? Now, before I distribute the limit, we can see that once I've grouped it now, the first group has something in common, right? Both terms of the first group have a g of x plus h. Similarly, the second group has a couple things in common, but it's something different now, right? In the second group, the f of x is in common, okay? So I can factor those out as well, and I can now write this as a couple of different limits here. So I'm going to factor this, but leave it all inside the first limit. So the first limit is going to be the limit of that first group, but I'm going to factor it, like I said. So it's going to be the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. I think I said I was going to leave it as a single limit, but then I distributed the limit as well. But this is always okay, right? So we've got all this here. Then we've got this plus sign right here. That needs to stay. And then we can look at the next product, right? So from the next one, I'm going to have the limit as h approaches 0 of the first term, which I've factored out. So I can factor out that f of x and then write the rest of it in its own limit. So the limit as h approaches 0, g of x plus h minus g of x, all divided by h. Okay? So just by adding and subtracting, or subtracting and adding the same term, doing some grouping and then some factoring, distributing the limit, we get to this point here, right? And so now these limits I propose are better, right? We know how to compute these. So as h approaches 0, the limit as h approaches 0 of g of x plus h, well, that just zeroes out the h. So this term right here, this what I highlighted in green, that just becomes g of x, right? What about the next one? Well, the next one, this is a limit of a difference quotient, right, of f. So this is where we go back to our assumption that f of x is differentiable. That means the derivative exists, right? Well, if the derivative exists, then it has to equal this difference quotient. So actually, this limit that's highlighted in blue, this is actually the derivative of f. This is f prime of x. All right? Once we get to the next term, everything's going to be the same. It's going to kind of repeat itself. Limit as h approaches 0 of f of x. Well, this one actually doesn't even have any h's at all, right? So this one is just f, so or f of x in this case. And then our argument for the last one here, this limit as h approaches 0 of g of x plus h minus g of x over h. Well, that's the difference quotient for g of x, excuse me, which we also assumed was differentiable, right? So now we've got another derivative here. This one's the derivative of g. So this is g prime of x. So in summary here, and that's it. Now we've done it, right? So in summary here, what we've shown is that the derivative with respect to x of the product function f of x times g of x is equal to the derivative of the first function. I'm just going to rewrite this first term, but I'm going to switch the order of the two functions. So it's the derivative of the first function times the second function, leave it alone, don't do anything to it, plus the first function, leave it alone, and now take the derivative of the second function and multiply that. So the derivative does not just go on each term, right? It distributes in this kind of weird way here, but this is called the product rule for derivatives. We have to obey this rule. All right, this is our product rule. And we know it works because we built it using the limit definition, right? So it has to work. All right, so let's do some examples now. Before we do some examples, you'll see what I just wrote there is, that notation is not too bad. But a lot of times we'll write this in a notation using letters that are generally not the names of functions. So another way to write this would be if we have two functions, u and v, and they're multiplied together and we want to take their derivative, then the product rule says take the prime of the first one, right, multiply by the second one, plus leave the first one alone and then multiply by the prime of the second one. So this is just kind of a shorthand way to rewrite the product rule that we just derived with f and g, just to write it in terms of u and v. All right, let's do those examples now. So here's our first example. Let's say we have a function. I'm going to swap out the x variable and just write this as a t, but what if f of t is equal to t to the sixth power times cosine of t? All right? Well, this is a product of two functions. What are the two functions? Well, the first function is the t to the sixth. The second function is going to be this cosine of t, right? And so we can make a little table here and we can say, all right, for this function, this f, our u is t to the sixth power, and our v is cosine of t. So can we take the derivatives of those individually, right? And yeah, of course we can. So we learned in the last class that u prime, so the derivative of a power function, we could put this through the limit definition, do all the work, but at the end of the day, this follows a simple rule that the power, that 6 there, that exponent, can jump down to the front, rewrite the t, and then the new power is 1 less than the old one. So the derivative of t to the sixth is 6 times t to the fifth. Okay, so that's our derivative of u itself. And then our derivative of v, well, we also learned using the limit definition and some limits that one that we proved in recitation and the other one that we're just kind of taking for granted, we worked it out to show that the derivative of cosine is always equal to minus sine. Okay, so that's one that you can always compute if you have to using the limit definition, but we'll see the derivatives of these trig functions all the time. So I recommend you memorize the derivative of cosine is negative sine. All right, now we have to put, this is v prime, okay? So now we have to put this together. So how do we do that? Well, f prime of t is now equal to, if you draw a table like this, if you make a table like I just did, then the product rule says to kind of crisscross multiply these. So it's going to be u times v prime. I'm going to write it out. Again, these are, what I'm about to write is kind of in the backwards order, but u times v prime, okay, plus, but order doesn't matter when you're adding, right? Plus the product of these two. So these two diagonal products, u prime times v. And as long as we write all this out, then this will be good to go. So the derivative of our function, f, is going to be u, which is t to the sixth, times negative sine of t. Make sure you keep this in parentheses since it's a negative sign, not a minus, but a negative, plus u prime, so that's 6t to the fifth, times cosine of t. Okay, and then we should always simplify this. The only thing here that we have to simplify is to move that minus sign out to the front. So f prime of t is going to equal minus t to the sixth power times sine of t plus 6t to the fifth cosine of t. Okay, now at this point, I'm going to put a smiley face and say that we're done. You could do some factoring. There's some stuff you could do with this, but as far as we're concerned, that's the end of this problem. That's the derivative of this function f. All right, let's do another one, and let's do this one maybe two ways, because that first one that we did, we had no way to do this one other than to use the product rule and to use it correctly, right? But we're still kind of, we believe the limit definition because we did all the work, but we're still kind of like just trusting that this kind of funny formula gives us the right answer, right? So let's do one where we can actually check it. So this one, let's say we have our y equals x plus 3 times x squared minus 2x. All right, and I want to take the derivative of this function. So one way that we can do it is we can do just like we just did. We can identify the two parts. This is a product of two kind of small functions, right, which are multiplied together to make this bigger function. And we can apply our product rule. So we can say our u is x plus 3. We can just take u prime now. So u prime is just going to be derivative of x plus 3, which is 1 plus 0. So that's just 1. And then our v, well, that's the other part of this function. So that's x squared minus 2x. And v prime is then the derivative of this. Remember, you can go term by term with these polynomials. Derivative of x squared is 2x, minus derivative of 2x is just 2. Okay, and so these are all the different pieces of our product rule. And then remember, we have to crisscross multiply and then add these together, right? Add these two together. So in computing all this, I'm going to write this out again. So our y prime is going to equal, I'm going to write it this way since this is what our table looks like, u times v prime plus u prime times v. And so just plugging in here, our u prime is going to be x plus 3 times 2x minus 2 plus 1 times x squared minus 2x. Okay? And this is perfectly fine. Again, just like on the last one, we could leave it this way. But because this is a polynomial, let's actually multiply this one out. Okay? So, again, this could be the answer. I mean, it is the answer. But I want to get this in a simplified form. So we need to distribute or FOIL these first terms. So when I multiply this out, this is going to be 2x squared plus what? 6x minus 2, so plus 4x minus 6. All right, and then over here we just add these terms. So plus x squared minus 2x. And then when we combine everything, we see that we have 3x squared, right, plus 2x minus 6. And so that's our derivative as a single polynomial in polynomial form, right? Standard form of the polynomial. All right, well, I said we were going to do this one two ways. Well, what we just did at this step was, these couple steps here, was to multiply everything out and get a polynomial that's in standard form. Well, can't we do that to start with at the beginning here, right? So let's go back and do that and then take the derivative the old way without having to use the product rule. So in other words, let's do the product first and then take the derivative. So multiplying this out first, I'm going to rewrite the function to start with. This is y equals x plus 3 times x squared minus 2x. And then do my distributive property here. So this is still y. I haven't taken any derivatives yet. This one's going to be x cubed plus 3x squared minus 2x squared minus 6x. So I can combine these middle terms on this one, right? So this then becomes y equals x cubed plus x squared minus 6x. And now I can take the derivative term by term of the polynomial, right? So now my derivative can be done as y prime equals derivative of x cubed. 3 comes down, leaves a 2 behind, so 3x squared, plus derivative of x squared, 2 comes down, leaves a 1 behind. Usually we don't write it, so 2x, minus derivative of 6x. Derivative of x is 1, so the derivative of this is minus 6, right? And we put this all together, and now we see that we got exactly the same answer both ways, right? So the product rule and just multiplying out and using our power rule by itself gave us the same answer, which is exactly what should happen. And so now we can put a big smile here. So that's exactly how the product rule should work, right? By the way, now you only have to do this one of these two ways. We only did this one twice to show that we get the same answer both ways. All right, so let's move on to the quotient rule then. So the quotient rule tells us how to take the derivative of a fraction. Again, I'm going to write this in terms of, I'm going to use the limit definition to work out the formula, and then we'll write this in terms of like u and v at the end. So for this one, I'm going to write the function as f of x divided by g of x, all right? And then we need to plug into our limit definition. So for this one, I'm going to leave a little room to kind of help us out. But our limit definition is then the limit as h approaches 0 of f of x plus h over g of x plus h. That's where the x plus h goes in. And then it's going to be minus f of x. Like I said, I'm going to leave a little room. Just a little bit on this one. Minus f of x divided by g of x. And then this is all over h. All right, so we want to perform a similar kind of trick of adding 0, so adding and subtracting the same thing to this one. But before we do so, I want to add these two fractions up. So the denominators are very similar, the g of x plus h and the g of x, but they're not equal, right? Because h never actually equals 0 when you take a limit as h approaches 0. So to be able to actually add these up, I need to multiply this first term by g of x over g of x, and the second term by g of x plus h over g of x plus h, okay? And so before I figure out what I'm going to add and subtract to this, I need to combine all this and write it as a single fraction now. So this is going to be the limit as h approaches 0 of f of x plus h times just g of x, and then I'm going to leave a lot of room here and write minus f of x times g of x plus h over here, all right? And then on the bottom, we have what? We have g of x plus h times g of x. That's our common denominator. And then we still have this h as well, right? Okay. So what do I want to add and subtract to this? Well, I want to add and subtract something that's going to be in common and kind of cancel out here. So I have a couple of options. What I'm going to do on this one is subtract out the product of f of x plus h times g of x plus h. All right, and then add in the same thing, f of x plus h times g of x plus h. And now when we do the grouping, it's going to be the same as what we saw before, right? So the grouping, we're going to group these two terms, and we're going to group these two terms, okay? Now, in the first one, what's going to factor out? Well, the f of x plus h is going to factor out, right? In the second one, what's going to factor out? The g of x plus h is going to factor out. Okay, and so let's see what we have when we do all this. All right, so this is going to become then the limit as h approaches 0 of, I'm going to factor a couple things out here. So the first one, the f of x plus h is going to factor out. And then this denominator of g of x plus h times g of x is going to factor out, all right? Times what's left here, I'm going to write this as a limit as well. Limit as h approaches 0 of g of x minus g of x plus h all over h, plus, same thing's going to happen with this second one. This will be now the limit h approaches 0, g of x plus h over g of x plus h times g of x. I'm not going to do any cancellation here, and we'll see why when we get to that point. And then times, this limit is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay, so kind of just like with the product rule, it's very similar to the product rule. Just like with the product rule, these first portions of these two limits, those we're just going to plug in h equals 0 and see what's left. Like I said, I'm not going to do any cancellation because we're going to put this all back together into a single formula. So I'm just going to leave it. What else do we have here? Well, this one, right, this limit of the difference quotient in terms of f, that one for f in terms of h, that one is the derivative of f. That's just f prime, right? What about the one for g here? So this one for g is almost the derivative of g, except there's one difference, right? And that's that these terms are in the wrong order, right? These need to be swapped. So actually this one is negative g prime of x, and this one over here is regular f prime of x. So when I write this all out now, because this is all added together, I can kind of move this over and put this at the beginning so that the positive term is first and the negative one is second, right? So when we do this then, I'm going to start with what I just wrote in the red box. What we have then is, we take the limits of the stuff that has, the stuff that I highlighted in blue. That stuff, we're just going to get rid of the h's, right? So that one's going to be g of x over g squared of x, so there's two of them, g of x times g of x, times on top f prime of x, right? So that's a positive f prime. And then when we add this up, we're now going to have a plus. This one's going to be f of x over g squared of x, g of x times g of x, times this one's going to be times a negative g prime of x. All right, so just pause the video here if you have to, work through this, make sure you agree with this. But I switched the order and then I just wrote out what everything's going to be. Now these two fractions have the same denominator, obviously, so I want to add them back up and I can distribute that minus sign. So at the end of the day, we end up with this single formula of g of x times f prime of x minus f of x times g prime of x, and then it's all over g squared. And this is why I didn't cancel anything here, specifically that g over g squared. So that leaves it in this form. Okay, so this is exactly the formula now. This is the derivative. Let's write it right here just to remind ourselves. The derivative of the quotient function f of x divided by g of x. All right, so this is it. This is our formula. But let's write this now with our u's and our v's, just so we can get kind of a simplified formula here. We want to take the derivative of u divided by v. So u over v prime. Well, according to this formula, this is low d high, so the bottom one times the derivative of the top, so v times u prime, minus high d low, so high d low is u times v prime, right? All divided by the bottom squared, right? So all divided by v squared. And so again, these are both correct. They're both exactly the same, but the one with the u's and the v's is sometimes easier for us to work through. Okay, so let's do a couple examples now, and then we'll see how it goes. So for our first example, I want to find an equation of the tangent line to this function. So the function is going to be y equals x squared minus 1 over x squared plus x plus 1. And I want to find the equation of the tangent line at the point 1, 0. All right, so we can double check that 1, 0 truly does lie on this curve, and you can check that on your own, but I'm going to say yes, it does lie on the curve. When x is 1, y is 0. So remember that the equation for the tangent line is always equal to this, right? So our tangent line is always equal to y equals f of a plus f prime of a times x minus a. So when we highlight everything here, our f of a is the height of our function. Our a itself is the input, right? And then our f prime of a, that's the thing that we need to calculate, right? That's the slope, that's the derivative. So what we need to compute is the derivative of this function at a, and then we'll have the equation of our line here. Okay? So let's use our quotient rule. Again, our y is equal to x squared minus 1 over x squared plus x plus 1. All right, so in this scenario, if we write this as a u over v, kind of like we did with our product rule, we'll call this the u and this the v. All right, and then we can write out, all right, our u is x squared minus 1. That means our u prime is 2x. We can just take the derivatives as we go, right? The derivative of x squared is 2x. Derivative of negative 1 is 0. Our v is x squared plus x plus 1. So our v prime is then 2x plus 1 plus 0. All right, and we need to plug this into this formula, the formula for the derivative, right? So our y prime is going to be v times u prime. So v times u prime is this way, right? V times u prime minus u times v prime. So that's minus this one, all over v squared. Okay, so if we put this all together, we have our first one, our v is x squared plus x plus 1 times u prime, 2x, minus u, x squared minus 1, times v prime, 2x plus 1, all divided by v squared, x squared plus x plus 1, quantity squared. Okay, and so there's a lot of work we could do here to simplify this and get it as a nice kind of simplified fraction. But for this problem, we only care about this at the point where x equals 1, right? And that's because we're asked to find the tangent line at that point, right? So we need the slope at that point. So when x is 1, we can just plug in and compute all this, right? So y prime when x is 1, this becomes 1 squared plus 1 times 2 times 1 minus 1 squared minus 1. I'm just plugging in 1's for x's here. All over 1 squared plus 1 squared. All right, and so if we very carefully work this out, we've got 3 times 2, so that's 6, minus 0 times 3, but that's 0, all over 3 squared, which is 9. So altogether, then a 3 cancels, so the derivative at this point is 2/3. All right, and so that is the kind of dark pink here. F prime of a, that's the value of f prime of a. Okay, so the derivative at this point, we take the derivative, use the quotient rule to do it, get it all correct, plug in x equals 1, we get our value of the slope, so the value of the derivative, and now we have to plug in to get the equation of the line, right? So remember, our y was equal to f of a plus f prime at a times x minus a. So our y is equal to, we already knew this was 0 plus 2/3 is our slope. X minus a, we know that a is equal to 1. All right, and so as usual, we should distribute this out, get a nice mx plus b slope-intercept formula for our line. So y is going to then be equal to 2/3 x minus 2/3. And that's the equation of the tangent line to that curve at the point. All right, so the quotient rule is great, but it is a little bit complicated formula. But what I will say is we don't always need it, okay? So similar to what we did with the product rule, let's say we have a function y equals x squared plus 3x minus the square root of x, all divided by x. Okay? I want to take the derivative of this. Well, I could use the quotient rule. So as a recommended exercise, I want you guys to use the quotient rule to get y prime. All right? But for this one, I want to know, like, do we need to use the quotient rule? Is there another way? Do we have to use the quotient rule, or is there another way to do it? And it turns out there is another way to do it, because in this case, unlike the previous one, so in our first example here, the denominator, the bottom, was very complicated. But on this one, the denominator is not so complicated, right? So we can actually break this one up and write this as a sum of individual fractions. X squared over x plus 3x over x minus square root of x over x. And then we can simplify each of these and write these as regular power functions. So x squared over x, well, that simplifies to just be y equals, x plus 3x over x, that reduces to just be 3. And then minus the square root of x over x. Well, that's like 1 over the square root of x. But in terms of a power function, we can write that as x to the minus 1/2. So remember, square root of x is x to the 1/2 power. If you then do the subtraction, right, then 1/2 minus 1 is negative 1/2. So I've rewritten the function like this. I haven't taken the derivative yet, but now to take the derivative, I just have to apply our power rule, right? And our power rule here is going to be pretty simple. So y prime is going to equal derivative of x is 1, derivative of 3 is 0, so that's gone, and then minus the derivative of x to the minus 1/2 is a minus 1/2 times x to the new power I have to subtract 1. So that's going to leave me with a minus 3/2 power. All right? And if I write all this out, then y prime is equal to 1 plus, I'll just write plus 1/2 x to the negative 3/2. And that's fine. That's the derivative. And that's pretty much as simplified as it can get. Okay? All right, I've got one more example for us, and then I'm going to leave you with 3 recommended exercises. But basically, we can use the quotient rule to compute the derivatives of the trig functions that we don't know derivatives of yet. All right, so I'm going to remind us, we have our trig functions, we have cosine of x, sine of x, right? And then from these two, we can build all the other trig functions. So for example, tangent of x is equal to sine of x over cosine of x. Secant of x is equal to 1 over cosine of x. Cosecant of x is 1 over sine of x. And cotangent of x is cosine x over sine x. Okay? So what I'm going to do is use the quotient rule to compute the derivative of tangent. And what you guys are going to do, and this will be on the test and on your next quiz, at least one of these, use the quotient rule to compute the derivative of all 3 of these. So individually, there's 3 recommended exercises there. All right, so here's how it works though in terms of the tangent function. So I want to know what's the derivative of tangent of x. All right, so we know that tangent of x is always equal to sine of x over cosine of x. So in this scenario, our u is sine of x. Our v is cosine of x. And we need to take the derivatives, right? U prime, the derivative of sine, we know is cosine. The derivative of cosine, as we saw earlier in this lecture, is negative sine of x. All right? And we just need to put this all together into our formula, right? So our derivative of tangent is going to be, remember it was v times u prime minus u times v prime all over v squared. So if we plug all this in, this is going to be sine of x times, so it's going to be, whoops, I wrote the wrong one. So it's going to be, it's v times u prime. So it's cosine of x, that's v, times u prime, which is another cosine of x, minus u, so there's our sine of x, times v prime, which is a negative sine of x, all over v squared. So v squared I'm going to write as cosine squared of x. All right. We can combine some stuff here. So in particular, we have a minus sign times a minus sign, so that's a plus. So this can all be written now as cosine squared x plus sine squared x all over cosine squared x. But now we can remember that the Pythagorean theorem, or really the unit circle definition of our trig functions, tells us that cosine squared plus sine squared is always equal to 1, right? So the Pythagorean identity then says that this is equal to 1 over cosine squared x. And technically this is true. This is the derivative of tangent, but you'll never see it this way because 1 over cosine x is actually secant x, right? So if we can replace 1 over cosine with secant and then square the whole thing, and this whole thing can then be written as secant squared of x. All right, so using the quotient rule, we have then now shown that the derivative of tangent of x is equal to secant squared x. All right, so you have to be able to do this by using the quotient rule, okay? But this is another one that we should just remember. We're going to take the derivative of tangent quite a lot throughout the semester, and we're just going to want to know this one. So, like I said, as a recommended exercise, compute these other 3 by using the quotient rule. Make sure you use the quotient rule to actually do the work. You can easily check online. This is an online lecture, so check online to make sure that your formulas match the actual answer, but make sure you can compute these using the quotient rule. That will be a question on the next test, guaranteed. Okay, guys, see you in class.